In this unit, we're going to look at finding volume for three-dimensional objects that are not rotated around an axis. And we're going to do that by looking at the cross-section of the object and see if we can find volume from there. So let me just show you an example. If I have a cone, for example, and I take a cross-section of this, and what I mean by a cross-section, that means just slice the cone perpendicular to the base. So if I just slice it, just cut across the top, if I take that slice out and turn it sideways, what I'm going to see is a circle. And what this cone is made of is a bunch of circles stacked on top of each other, and each circle gets progressively smaller as we go from the bottom of the cone to the top. So what the idea behind looking at volume by cross-sections is that I would need to find the area of one circle and then add the area of the next circle and add the area of the next circle and add the area of the next circle. So basically what I'm doing is like stacking pancakes, if you will. In this case, because my cross-section is a circle. So I would take a bunch of pieces of paper or pancakes or something really, really thin. So maybe not pancakes, but maybe a piece of paper. And if we've got circles that are getting smaller and smaller and we stack them on top of each other, it makes a three-dimensional object. So if we could find the area of each circle, add all of those circles together, that will give us the volume of this cone. So that's one way to find the volume of an object that's maybe not being rotated, is if we can find a cross-section, find the area of that cross-section, and then find an infinite number of those. Let's see if I can put this to an example, but this is the premise of volume by cross-sections. So let's see if we can put this to an example. We're going to find the volume of the solid that has a base bounded by those four graphs. And I'm going to do different kinds of cross-sections. So first of all, the area bounded by there, I've graphed that already. We know that this one is y equals x squared plus 1. I know that this is y equals 0. This is x equals 0. And this one is x equals 3. The cross sections are going to be squares this time. So we're going to create kind of a different looking shape. And I'll show you what that shape looks like in just a moment. I'm going to try my attempt at drawing squares perpendicular to the x-axis. So here's the hard part for me, is trying to draw this so that it looks 3D. So when I'm drawing this square, I'm going to draw one base of it, and the base is perpendicular to the x-axis. So there's one side of my square. The rest of the square then is going to literally come vertically out at you. And it's really difficult for me to draw something that is vertically coming out of the page. But imagine that this square is standing on top of the base that I have drawn. And if we put an infinite number of these squares, what I can see is happening is that each square is getting smaller and smaller if we look from right to left. If we look on the right side, we've got some really large squares, but if we look on the left side, the squares are getting smaller and smaller because the shape itself is starting to shrink. So imagine that there are an infinite number of these squares, all stacked vertically, so coming straight out of the page at you, and these squares are perpendicular to the x-axis. Now, if you're not seeing it there, let me try using that app that I've used before. So this is the same base. You can see the base on the bottom of my picture here. The base is the x squared plus 1, x equals 3, x equals 0, y equals 0. So what I'm going to try to do is, I'm not sure how to shrink that bottom image. But what I can show you now, though, is what's going to happen when I do that. You can see that I get this interesting shape. And you can see that the squares are getting smaller and smaller as I go from right to left. So I've got this, there's the large square that's on the far right, that's a 3 by 3 square. And then there on the left is the left-hand side of my shape. So they can see that's a 1 by 1 square. And then there are an infinite number of them. So this is the 3D object that's created by having square cross sections on that base. Kind of strange, but you've seen shapes similar to this in buildings and amphitheaters, things like that. So what we're going to do now is find the volume of this three-dimensional area. Okay, let's go back to the picture here. So what I need to do then is find the area of one square, one representative square, and then I can use that and integrate in order to determine what the volume is. All right, so one square, I need to find the area of one square. So the area of one single square is base times height. So what we need to do is figure out the base and height. Now, the base and height are changing depending upon where we are on the function. So that means the side of the square is dependent upon the function itself. That means the side of this square is x squared plus 1. And since it's a square, that means the height of the square is also x squared plus 1. So that means the area of 1 squared is x squared plus 1 square. That's one square. Now if we put an infinite number of them, we're going to integrate. So the volume then of the shape is found by integrating, and since everything is perpendicular to the x-axis, we're going to use the x-axis to determine the bounds. That means we're going from 0 to 3. And we will just take the area of this one square and find it an infinite number of times between 0 and 3. All right, so we cannot use u substitution here because if u is x squared plus 1, du is 2x dx, and we do not have a 2x dx in here, so we cannot use u substitution to find the antiderivative of this. So we're going to go back old school, and we're going to actually multiply x squared plus 1 by itself to get a polynomial. So this is now x to the 4th plus 2x squared plus 1. Now I can just find the antiderivative using the power rule. 1/5 x to the 5th plus 2/3 x cubed plus x, and I'm going to integrate that from 0 to 3. 3 to the 5th power is something big, and I'll let you do that part. So this is 3 to the 5th over 5 plus 2 times 3 to the 3rd is 27 times 2, so that one is 54 over 3 plus 3 minus, if I plug 0 into everything, I'll get 0. So there's my final answer. This is the volume of that three-dimensional shape. Okay, using cross sections. All right, let's go on to another example. I'm going to use the same base, but I'm going to use different cross sections. So this time we're going to use squares that are perpendicular to the y-axis. Let me refresh my memory what the function was. Y equals x squared plus 1. Okay, this time square is perpendicular to the y-axis, so that means my square is going to be in this direction. And imagine this three-dimensionally coming out of the page, and then we're going to have an infinite number of these squares coming out of the page. So they're moving vertically instead of horizontally. In order to find the length of the side of the square, I know that from here to here, this length is 3. And I know from here to here is some x value based off of the function itself. So just like we did in the last section, we're going to use this y equals x squared plus 1 and isolate x. So x equals, really it's plus or minus the square root of y minus 1. But since we're only looking at one side of this, we're only going to use the positive of the square root of y minus 1. Okay, so to find the length of one side of the square then, it's going to be 3 minus that x value. So 3 minus the square root of y minus 1. And the area of the square then is 3 minus the square root of y minus 1 squared. Everything is with respect to y, so we're going to integrate along the y-axis from 1 to 10. And why didn't I start at 0? Because we've got a really interesting situation here. We have a different part of our graph So that means from 0 to 1, we've got a completely different thing going on. But let's just look at from 1 to 10 first. So from 1 to 10, I can see that the side of the square is changing constantly because this curve right here is always changing. So from 1 to 10, the squares are changing in their size. However, from 0 to 1, those squares are not changing at all. Every single square that is perpendicular to the y-axis, and we're going to put an infinite number of them, every single one of them has a base that's 2 units long. So from 0 to 1, to find the area of those squares, each one is 2 times 2, and we'll go from there. I'm going to be honest with you, this one is not super pretty to... Oh, it's okay. Let's integrate it. Let's do it. So I'm going to square the 3 minus the square root of y minus 1. So 3 squared, that's 9, minus 2 of these. And then the square root of y minus 1 times itself is just y minus 1. If I simplify that then, 9 minus 1, so I end up with 10 minus 2 times the square root of y minus 1 plus y. If I find the antiderivative, that's 10y. This is 2 times the square root of y minus 1 is this. So the antiderivative, because the derivative of the inner function is just 1, then I can use the power rule or even use substitution, and it's not going to change anything. So add 1 to that, that's 3 halves. So this is 4 thirds y minus 1 to the 3 halves. And finally, this is 1/2 y squared. And we'll integrate from 0 to 10. I'm going to let you do that. Okay, this final one, this last one on the end, so that little rectangle at the very bottom, 2 squared is 4. The antiderivative of 4 is 4y. Yes, there are many different ways of doing that, but this is how I'm going to do this one. Okay, I'm going to let you finish that one. You can plug in 10 and plug in 1 and subtract. And then for the 4y, you can plug in 1 and plug in 0 and subtract. It's the setup that's the interesting part. Okay, let's move on to the last example. We're going to use the exact same shape, but this time we're going to put equilateral triangles perpendicular to the x-axis. Holy cow. So let's look at these equilateral triangles. Equilateral triangle, not great. You get the idea. I'm going to have a bunch of triangles that all have the same lengths of sides, and they're all going to be stacked infinitely. So we know the height of, or one base of the equilateral triangle. So I'm just going to draw one equilateral triangle. We know the base is x squared plus 1. And we know, since it's equilateral, these are all x squared plus 1. In order to find the area of one triangle, we need to do 1/2 base times height. Well, we know the base is x squared plus 1, but how tall is this triangle? So in order to do this is a equilateral triangle. We know that all angles are the same, 60 degrees. So that means this is 30, and this is 90. Well, we know quite a bit about a 30, 60, 90 triangle. First of all, when I split that down the middle, I know that this part of this 30, 60, 90 is half of x squared plus 1. And then in order to find the height, I didn't leave myself enough space. Because this is a 30, 60, 90 triangle, the height is this side, the side opposite 30, times the square root of 3. Gross, but not bad. So let's look at the area of this triangle. 1/2, the base was x squared plus 1, and the height is root 3 over 2 times x squared plus 1. So if I simplify that a little bit, the square root of 3 over 4 times x plus 1 squared. So there's the area of one equilateral triangle. And now if we integrate that from 0 to 3, since we're looking at the x-axis, we would just find the area of an infinite number of these by integrating this from 0 to 3. And we pretty much did the same work up above, so I'll let you finish this one too. Okay, that's the gist of this, and different shapes could happen. We could put semicircles on this, and you would just find the area of half of a circle and infinitely integrate that as well. Okay, go give it a try.